Let us turn now to the fact that light is bent by the gravitational force of a very massive object. As we know, we can escape the gravitational attraction of the Earth by launching a rocket with sufficient velocity. This is called the escape velocity. However, we can imagine an object so massive that not even light can escape the pull of gravity. If one compresses enough matter into a small space, then the force of gravity will be so strong that even light cannot escape. It will be bent back towards the massive object. To someone on the outside, this massive object will appear black, since light cannot escape. It is called a black hole. If we take the Earth and compress it into a tiny sphere with a radius of 1 centimeter, then it would become a black hole. If all the mass of the Sun were compressed into a sphere of radius 3 kilometers, it would form a black hole. Einstein's theory of gravity predicts the existence of black holes. Indeed, when a star with a mass more than 3 times that of the Sun collapses under its own weight, it will end its life as a black hole. However, one may ask whether black holes actually exist in our universe. Observations over many years have led to convincing evidence for the existence of numerous black holes scattered throughout the universe. There is strong evidence that a supermassive black hole lies at the center of our own Milky Way galaxy. Its mass is estimated to be about 4 million times larger than our own Sun. The size of this black hole is 7 million miles. In effect, this means that if one travels closer than 7 million miles to the center, one will lose contact with the outside world. One will no longer be able to communicate or send light outside. In effect, one is trapped inside the event horizon. Although the black holes in our universe are incredibly large with a very strong gravity, they hold within them the secrets of the universe. If we wish to understand the structure inside the event horizon, and very close to the center of the black hole, then we must apply the laws of quantum mechanics. In the 1970s, Hawking demonstrated that quantum theory predicts that black holes are not truly black. In fact, they emit energy as electromagnetic radiation at a certain temperature. This is called the Hawking temperature of a black hole. Since Einstein showed that energy is equivalent to mass, this means that the black hole will lose mass and eventually evaporate. This remarkable scenario is called black hole evaporation. In order to put things in perspective, let us consider a stellar black hole whose mass is the same as our Sun. As we have seen, the distance from the center to the event horizon is only 3 kilometers. A black hole of this size has a Hawking temperature of only 60 nanokelvins. This is only 60 billionths of a degree above absolute zero. If such an object were placed in our universe, then it would be colder than the temperature of the cosmic microwave background. Therefore, it would heat up and grow rather than shrink and evaporate.